Okay guys, today we're going to talk about strong acids and strong bases. I'm going to show you a couple more forms of calculations, and that will be it for today. Some things that I just kind of want to review, I want you to think about, I want you to remember. First of all, when we talk about aqueous solutions and how they react within an equation, we have to be aware of all of that depends on the pH of the solution. So depending upon the pH of the solution, it drives the reaction in a certain way. We need to remember that pH relates to the way a reaction happens. So we can figure out a lot about that reaction by looking at the acid-base concentrations, and that lets us figure out, like we started to last week, about the way that my equilibrium is going to shift. Does it lie with the reactants? Does it lie with the products? Is it continuous, or does it begin and end? Do I have a reversible reaction arrow, the arrow going both directions, or do I have an arrow going just one reaction? If I have an arrow going just reaction one way, I know it doesn't reverse, that it's not constantly happening. So we have to keep all of those things in mind. When we look at all of these things, remember that the simplest things to work with are the strong acids and the strong bases. So I'm going to start with them first, and we'll work through the problems that involve those things before we go into our weak acids and our weak bases. Remember, if I have a strong acid or a strong base, then I have strong electrolytes, which tells me that I have ions in solution and pretty much 100% dissociation. I'm just going to say 100% D for dissociation. Also, we've talked about there really aren't that many strong acids and strong bases, especially strong acids. There are more strong bases because those are those hydroxide compounds, ionic compounds that contain hydroxide. But still, keep in mind that our really strong ones are our alkali metals, and those heavier alkali metals, as we move to the bottom of that column on the periodic table, some of those are insoluble. So we don't do a lot of reaction examination with those. They can serve as part of an acid-base reaction, but they're much less likely to do so. So most of your problems are going to be concerned with alkali metal hydroxides if we're talking about bases, and they're going to be ones that are a little bit towards the top of the group of alkali metals. All right. So moving right along with our strong acids and strong bases, I'm going to talk about strong acids first. Before all of those things, we were talking about acids and bases both. So you should remember that you have 6 monoprotic strong acids, which means they can donate 1 hydrogen ion, or we call them 1 proton. They're a proton donor. You have 1 diprotic. That's your H2SO4. So H2 tells me it can donate 2 hydrogen ions, or it's a donator of 2 protons. If I have a strong acid in aqueous solution, I'm going to use this as an example. I've got my nitric acid, and when that dissociates, I end up with H3O plus, my hydronium in aqueous solution, plus my nitrate in aqueous solution. Now you're going to see these reactions written this way. You have to understand, it should be understood that it's in H2O. Even though it won't always be written as part of the reaction, technically speaking, this is really plus H2O liquid. So we have to remember that. And when this happens, when I put this nitric acid in water, I have complete dissociation, complete ionization, complete dissociation of my ions. So I end up with my H3O plus and my NO3 minus. This might also be written, rather than writing it out this way, it might also be written as H plus plus NO3 minus. And we just have to understand that those things are interchangeable. So I wanted you to be aware of that, so that if you see an equation that looks like that where the water's missing, you're not like, well, how did that get there? There's no water in the equation. Or why is this just H plus? What happened, to my other two H's? You have to understand those things are interchangeable. If I have a strong acid in aqueous solution, then 99.999% of the time, it is the only source of my hydrogen ions. So I know that they're all coming from whatever that strong acid is. So when we work with this stuff, we're going to be calculating pH. If I have a monoprotic acid, then it is really quite easy to calculate or to find my pH. Remember that H plus tells me the concentration, or is equal to the concentration of the original acid. The concentration is usually given. Now, there might be a case where you're told like 15 grams of this is diluted in 1,000 milliliters of water. Well, then we just go back to our old molarity, grams per mole, and we figure out the molarity of the solution, and then we move forward with our concentration, because our concentration equals the molarity of solution. So if you are given grams in liters, you may have to calculate the molarity. We've done that already this year. Multiple times. You've had to do it in lab. We've done it in problems. You shouldn't have any difficulty doing that. So don't let that throw you if it shows up in a problem. If you don't remember how to do that, you need me to go over it, then just reach out and I'll plop an example on Classroom, or we can get together and I can go over it with you. But remember that when you get into working those problems. Okay, so the concentration of the acid given is equal to the concentration of the hydrogen or hydronium ions. So let's say I'm given a 0.20 molar nitric acid solution. And I first need to examine that, and I need to say, okay, so I've got hydrogen and I've got nitrate. And if I look at this and I isolate them, this is a 1-to-1 ratio. So if my H plus concentration equals the concentration of my strong acid, then whatever my anion counterpart is, it also equals the concentration of the acid. So I can say that my H plus concentration is equal to my NO3 minus concentration. And I know again that my H plus concentration equals the molarity of the acid. So I can say that 0.2 molar is equal to my H plus concentration, which is equal to my NO3 minus concentration, because again, 1-to-1 ratio. So I can say that the concentration for both parts of my solution is 0.20 molar based on the ratio of cation to anion or hydronium ion to anion counterpart in one of these monoprotic acids. So concentration of both is 2.0 molar. I can move forward with that when I'm calculating my pH to figure out the pH of the solution. So let's look at an example problem. Calculate the pH of a 0.04 molar solution of aqueous HClO4. So we're going to start this by number one. What type of ratio do I have present? Here's my hydronium. 1-to-1. I've got a 1-to-1 ratio. So I know I can follow the same thought pattern. My hydronium ion, or my H plus concentration, is 0.040. That is equal to my ClO4 minus concentration, which means both of them have a molarity of, should be a 0 there, 0.04 molar. I can use that to find the pH. Remember, pH is equal to the negative log of the hydronium ion concentration. So I can say pH equals negative log of 0.040 molarity, or my pH equals 1.4. Now I can look at this, and this is one thing you should always do at the end of one of these problems. I want to look at this and I want to look at where it falls on the pH scale. I know that I have hydrogen present up here. If hydrogen is present, then I know I'm starting this with an acid. So I would expect my pH to fall somewhere in the range of acids. And what happens here, once I get my problem finished, I see that I have a pH of 1.4, which checks because that would be an acidic solution. So I know that I'm on the right track. Okay, so now let's look at, let's examine our strong bases just a little bit. So if I'm dealing with strong bases, the most common type of strong bases, and I already said this, are my ionic hydroxides, where I've got a cation here and my OH minus anion. The most normal way that I find these is an alkali metal plus a hydroxide. Said that at the beginning too. And again, just like I talked about with the strong acid, if I have a strong base, it's going to completely dissociate into ions in aqueous solution. So if I have a 0.3 molar solution, let's examine this. Here's my cation, here's my anion. I'm looking at it again. I've got a 1-to-1 ratio. That's great. That tells me I have 0.3 molar Na plus concentration and 0.3 molar OH minus concentration. When I have that in solution, because it's a strong base, I can say that I have no undissociated ions. I assume 100% dissociation. So let's look at this a little bit. I'm going to show you, we can set these up pretty much just like I went through with our acid, our strong acid, but I'm going to show you there's two different methods. And I don't really care which one you use. Whichever one is easier for you to remember, then go for it. So here's your question. What's the pH of a 0.02 molar solution of NaOH? So I have two possible methods. In the first method, I calculate the H plus concentration using my OH minus concentration and my Kw, and then I use that. Once I have my H plus concentration, I can plug that into my log and I can find my pH. So let's look at it this way. I'm going to start with my Kw equals OH concentration times H plus concentration. The reason I wrote my OH first is this time we're dealing with a basic solution. That's not a requirement. It doesn't matter which way. It's just, it's a multiplicative. So either way you write it, it's going to be fine. So I start with my Kw because remember, these are still in aqueous solution, so we're treating it like a water solution. So I've got 1 times 10 to the negative 14th equals 0.028 molar. This would be my OH minus times my H plus. So if I, manipulate my math and figure out what my H plus is equal to, I find that my hydronium ion concentration is 3.6 times 10 to the negative 13th molarity. So I have this. I now have my hydronium ion concentration. I can plug that into my pH log and I can figure out my pH. So I take that and I say pH is equal to the negative log of my hydronium ion concentration, or pH equals negative log times 3.6 times 10 to the negative 13th molarity, H plus, pH equals 12.45. I look at that again and I go, okay, I started off with this solution, NaOH. The OH tells me it's a base. I would expect in the end to find a basic solution. My pH should fall in that range. And it does. So I have a basic solution. So my math has checked out. So that's the first method. Second method is a little different. And I don't care which one you use when you do these problems. Whichever one seems quickest to you or makes the most sense. The second method, I find my POH, my quantity or concentration of hydroxide ions. And then I use that with my formula for finding pH, the 14 equals pH plus POH. So let's see what happens when I do it that way. My POH is equal to the negative log of my hydroxide ion concentration. And my concentration was 0.028 molar, so I take the negative log of 0.028, which gives me a POH of 1.55. I can plug that in then to my pH equation where 14 equals pH plus POH. Then I can plug in my POH because I know it. This is a known now. So I plug it in, do a little math, and I end up with my pH equals 12.45, which is exactly what I got the other way. I personally don't think one's any easier than the other. We could argue that. It doesn't matter to me which way you do it, but I just gave you a couple choices. Again, basic solution. I started with a base. I end up with a base pH, which is what I would expect to have happen, or would hope would happen anyway. So the next thing we have to think about, because it's been lovely that these have all been 1-to-1 ratios, but guess what? You're not always going to have a 1-to-1 ratio. We know, let's look at maybe my sulfuric acid, H2SO4. That's not a 1-to-1 ratio. And if I start to look at some of my alkali metals, they're not all 1-to-1 ratios. So it's possible to have, in order to get a neutral ionic compound that represents an acid or a base, I may not have an exact 1-to-1 ratio. So I have to look at that. So let's look at a problem that looks like this. Find the pH of a 0.0011 molar solution of calcium hydroxide, CaOH twice. So immediately when I see that little subscript, that should be like a light bulb going off in my head. Okay, let's look at my ions. CaOH. This is not a 1-to-1 relationship. This is a 1-to-2 relationship. So I remember I'm going to have to deal with that when I move on to my problem. I'm going to write down what I know. I know my molarity is 0.0011 molar. So I can treat this the same way, and I can say, okay, so I know my concentration of calcium is equal to the molarity, so my calcium is 0.0011 molar. If I had just one hydroxide, it would be equal to 0.0011 molar, but I don't. I have two of those, so it becomes a simple multiplication problem to get the concentration of my hydroxide ions. So I multiply and I find out that my hydroxide ion concentration is 0.0022 molar. I can then use that and I can plug it into my equilibrium constant equation with my H concentration times my OH concentration. Plug in what I know. I know my Kw for my aqueous solution. I don't know my hydronium ion concentration, but I do know my hydroxide ion concentration, which allows me to work this equation, manipulate it to get H plus by itself. When I solve, I end up with a molarity, with a concentration of 4.5 times 10 to the negative 12th hydrogen ions or hydronium ions. So that's working through the math of that part. Then I can just put it into my pH formula. My pH equals log of my H plus concentration. And when I do that, I have pH equals negative log 4.5 times 10 to the negative 12th. Plug it into your calculator and you should see that your pH is equal to 11.35. I started with CaOH twice, calcium hydroxide. I know because it's got the hydroxide there that I'm starting with a base. So I'd expect my pH to be in base range when I'm done. And guess what it is? It's a basic solution. So that lets you work with both a strong acid and a strong base, and it shows you how to work through the steps of finding the pH or the concentration, the ion concentration for either case. The last thing I want to talk about just a little bit, this actually, I'm looking at this and I'm seeing a mistake right here. This should actually say when I'm dealing with strong bases, and I said this at the beginning, but I didn't have it written down, so I want to be sure that you get it to write it down, are all alkali metal hydroxide. They're strong bases. They're strong electrolytes. We probably should also add in here that these guys are strong conductors, just like my strong acids are. We also have some other strong bases that are formed when I have a reaction with water that takes place. We know anytime we have water, not only do we have the possibility for this H3O plus, we also, if we're talking about a basic solution, have the possibility for that OH minus to show up. When I have something that's going to form a basic aqueous solution, then there are no O2 minuses left in that solution. Remember, this is a plus and a plus, H plus, H plus, plus O2 minus in order to get my neutral water. So when I have a base in solution, essentially I have no O2 minuses, no oxide ions left in that solution. When those oxide ions react with water, I end up with 2 hydroxide ions. So there's no free oxygen normally floating around in these solutions. And that's just a little overview. Like I said, I've left you some problems to do today. That'll be your assignment for today and tomorrow. I'll post one more new thing on Wednesday. On Wednesday, I'm going to talk, my plan is to talk about weak acids and weak bases and to leave you some problems. And then on Friday of this week, we'll get together for a wrap up and I'll answer any questions. If you do have questions over the problems that are assigned today and you need me to work any of them, send the numbers to me and I will do that on Friday during our Google Meet. And that's about it, I think. Have a great day, you guys. Talk to you later.